discussed that for the depletion load inverter, the salient voltages should be found by resorting to iterative procedure. Okay, so let us take up one numerical problem. So here you see that we need to calculate the critical voltages, namely the nominal output load VOL, VOH, VIL, VIH, and find the noise margins of the depletion load inverter circuit. So these are the data. So power supply equal to 5 volt and 0 bias threshold voltage of the driver transistor is 1 volt. 0 bias threshold voltage of the load transistor is minus 3 volt, because these are depletion depletion NMOS transistor. Okay, and the aspect ratio of the driver is 2, whereas that of the load is 1/3. As you can notice that this being a mere load, okay, its width to length ratio is kept much lower than that of the driver, so that it cannot unduly interfere in the operation of the driver. Okay, and the process transconductance, that means the product of mobility and gate oxide capacitance per unit area is 25 microampere per volt square. Gamma, the substrate bias coefficient, is 0.4 v to the power 1/2, and the electrostatic Fermi potential of the p-type substrate is minus 0.3 volt. So first, as we need to calculate VOL, note that the output voltage I equal to 5 volt. Okay, this need not be no explanation is required. Acha, here note that the ratio of K load by K driver, it is this. It is found to be 1/6 in the present problem. And to calculate the nominal output voltage low VOL, okay, this is the expression that we got from solving the quadratic on VOL. And remember, this is also a very important equation. That means the threshold voltage of the load device does vary on the output voltage. Equation 1 and equation 2. So based on iteratively using equation 1 and 2, we can find out the value of VOL. First iteration is that assume that Vout equal to 0. Okay. Certainly this is not, but this is the starting assumption. So based on that, we can calculate the threshold voltage of the load device, that is obviously minus 3 volt. And now you calculate VOL by applying equation 1. So here we get that is 0.192 volt. So then we need to refine the solution. In the second iteration, what we get, the threshold voltage of the load device happens to be this. That means equation 2. So here obviously Vout is no longer 0, it will be 0.192. Putting the value and the other parameter value, we get the refined value up to VT load equal to minus 2.95 volt. Okay. So obviously, as the source is no longer connected to ground or source is no longer connected to substrate, so obviously the actual threshold voltage of the load device will be more positive compared to the 0 bias threshold voltage, which is minus 3 volt. So here we have got it to be minus 2.95. After that, what we can do, we can make it a more accurate result. So what we do, putting this value of VT load, we can recalculate VOL. We find it to be nearly 0.186 volt, and then VT load is found out to be minus 2.95. So as the threshold voltage of the load device stabilizes at minus 2.95, we can take it as the final value, and so VOL remains as 0.186 volt, right? So next, to calculate the lower salient input voltage VIL, we need to solve the relevant equations. What are they? That means equation 3 together with 4 and 2. What are they? So first, equation 3 is obtained as we did in the earlier class, that based on the current voltage equation at the output node. Okay, and then differentiating these with respect to input voltage and setting dV out d equal to minus 1 at V input equal to VL, we got this expression. And also this is the output. Sorry, this is the current equation. Okay, so this is the current through the depletion load device, and this is the current through the driver enhancement mode transistor, which is in linear region. Okay, so in VIL, we need to solve these 3 and 4, but keeping in mind that the threshold voltage actually depends, the threshold voltage of the load device does depend on Vout. Based on that, we can carry on the solution. Okay, so then, yeah, right. So how to do that? yeah, first iteration is what? V out is slightly lower than V out. If you recall the voltage transfer characteristic at VIL, the enhancement mode driver transistor has just started to conduct. So output voltage is not much below the VOH. You can, as first iteration, we can assume it to be 5 volt. So with that 5 volt, what we do, we calculate the threshold voltage of the load device. It is found to be minus 2.36. Putting this in equation 3, that means here we can get a implicit relationship of VIL in terms of the output voltage. Okay, so output voltage can be made in this fashion. So only two unknowns are there, namely output voltage and the corresponding input voltage. We solve them by simultaneously solving this equation and the current voltage equation, this one, because we know the other numerical values. So what we get, the output, first the VIL value, we get it to be two choices are there for solving the quadratic, but obviously VIL is definitely somewhat higher than the threshold voltage. And what is the threshold voltage of the driver transistor? That is given to be 1 volt. So 0.98 is not admissible. We take the 1.36 volt solution. Okay. So assuming this to be the solution, next what we do, we have to refine the value of VIL. So we get it to be, say, output voltage first we obtained it to be 4.81 volt. It is slightly lower than VOH equal to 5 volt. Then in the second iteration, okay, what we do, we recalculate the threshold voltage of load device. We get it to be minus 2.3. Earlier was minus 2.65. Okay. So earlier it was minus 2.36. Now we get it to be minus 2.38. Okay. More positive, right? And earlier VT load equal to minus 2. So difference in, okay. Now the question is that we can refine it more, but as the difference is just 20 millivolt, we can stop the iteration for practical purpose. So take VIL to be 1.36 volt as a more or less acceptable estimate of the VIL. Next, how to calculate VIH? Note that in the voltage transfer characteristic, VIH is above the 50, it has crossed the 50% swing of the voltage, input voltage, and also the output voltage has come quite below, slightly up higher than the VOL. Okay, right. So what we do here, and there has been a sharp slope, okay, of the output variation with respect to input. So VIH, we take this, and now we have to take into account the slope of the variation of threshold voltage of the load device with respect to output voltage. We no longer can neglect it, right? So now 4 equations will be involved while trying to calculate VIH. What are they? First of all, see this DVT deload. Okay, then this will be involved, equation 6, and of course VIH, this value. Okay, and of course the VT load. So 4 equations are involved. So as before, we assume first that although actual output voltage is slightly higher than 0.2 volt, so our first guess about the output voltage is, let us keep it to be same as VOL. Actually, it will be slightly higher, as we shall see shortly. So with the assumption that output voltage equals VOL, that means 0.2 volt, for input voltage equal to VIH, what we do, we calculate VT load first. Okay, it is obtained to be minus 2.95, and then the slope of the threshold voltage of the load device variation with respect to the output voltage, that is found to be 0.22, because we know the value of gamma, we know the value of phi f. The output voltage, we have kept it as 0.2 volt. So then, on finding this slope of threshold voltage load, okay, with respect to the output voltage, what we do, we put it in the equation of input voltage, the VIH. So here we get the implicit relationship between output voltage and the input voltage. So through the simultaneous equation, that means the KCL current equation and this equation, we solve for VIH and output voltage. So what is the VIH? As we can see, 2.43 volt. Okay, so 2.43 volt, and but you can say that with the output voltage equal to 5 volt, with the power supply voltage equal to 5 volt, this is less than 2.5. So yes, there can be some asymmetry in the actual design. Okay, so it is 2.43 volt, but ignore the impossible value, negative value 0.35. Now what you do, we calculate V out, we found it to be 0.67. Okay, justifiably it is above the VOL. VOL, as we recall, we found out to be, I think, what was the value we got? That was, yeah, 0.186. So obviously 0.67 is above 0.186. What we do, recalculate threshold voltage. Earlier was this. So as before, we recalculate the slope from 0.18, it is refined to 0.22. Also the threshold voltage, it is refined from minus 2.95 to minus 2.9, and we recalculate VIH, we find it to be almost same as the input voltage. Okay, here actually we are doing the calculation using our calculator, so I did it. But if you have got computer, we can do more accurate, say correct up to 3 place or 4 place. Anyway, so the basic thing is that we need know the solution procedure, the iterative solution procedure. So the stabilized value of the salient voltages of the input ones are VIH equal to 2.43, VIL was 1.36 volt, and VOL is 0.16, VOH equal to 5 volt. So as you can see, the noise margin we can calculate. Okay, so VOH minus VH equal to 2.57, NML equal to 1.174, noise margin on the lower side. So this is about how to analyze a problem given the values of the power supply, then the aspect ratio of enhancement mode transistor and load device, also the process transconductance parameter and the other parameters like gamma and say phi f, all these. Okay, so we know how to arrive at the uh, justifiable values of the VOL, VIH, VIL and uh, VOH. Okay, and calculate the noise margin. Okay, so now next what we do, so far we have seen the inverters that we have been taking into consideration. The driver plays a very central role in trying to control the output voltage, okay, based on different input voltages. Okay, and there is a load device. The load can be either passive or it can be an enhancement mode transistor or a saturation or linear or else a depletion load NMOS transistor. But now we are taking a complementary push-pull operation. That means we have got two drivers. One is a PMOS transistor, the second one is a NMOS transistor. And the NMOS transistor plays the role of the driver towards the higher side of the input voltage. Okay, when it is in the linear region of operation and it can dominate the operation, that means it can try to pull down the output voltage level. Whereas towards the lower range of the input voltages, it is the PMOS transistor that plays a central role. It acts like a driver while the NMOS transistor acts like a load. Okay, that means for the lower side, PMOS transistor being in the linear region, it can control the output voltage level. But NMOS transistor offers high impedance, it is in the saturation or cutoff, so it cannot play any role. Its role becomes insignificant towards the lower range of the input voltage. Okay. So in the CMOS inverter, that means complementary metal oxide semiconductor, metal oxide semiconductor inverter, the complementary push-pull configuration is evident. For high input, NMOS transistor drives or pulls down the output node when PMOS transistor is the load, and for low input voltages, PMOS transistor drives the output node while NMOS transistor behaves like the load. What are the advantages of CMOS inverter over the other configurations? Steady state power dissipation is negligible. That means when the input voltage is nearly power supply voltage, okay, it is through the operation of this NMOS transistor that it is almost equal to 0 volt and no current conduction takes place between the power supply rail and the ground rail. And similarly, in the other stable region, that means when input voltage is nearly 0, when only P transistor provides a channel, whereas NMOS transistor is cut off, the output voltage is perfectly VDD. So at that point of time also, no current conduction takes place between power supply rail and the ground rail. Okay, so steady state power dissipation or DC power dissipation is negligible. But for the leakage currents, yeah, leakage current actually they play they become important as we shall discuss about the latch-up effect also. That means the leakage currents is due to the reverse bias uh, PN junction. Okay, for the NMOS transistor, you recall the P-type substrate is there, and N plus source and drain are there. So that PN plus junctions, two such, okay, they conduct leakage currents. That means when they are reverse bias, still some current flows. They are very negligible. But with the with the increase of temperature and other ambient conditions, the leakage current can become not too insignificant, and some power dissipation can take place. So that means when we take the correct value of power steady state power dissipation, the power dissipation because of leakage currents may need to be considered that point of time. Okay, particularly as we shall see later on when we shall take up the power dissipation through inverters in more details. Okay, but now, for the sake of simplicity, we'll assume that the DC power dissipation is fairly negligible. Okay, we can take it to 0. Second advantage is that the voltage transfer characteristic shows a full output swing. That means it gives us a wide noise margin, probably the widest noise margin possible of all the inverters. Okay, why? Because VOH is perfectly VDD and VOL is perfectly 0 volt. And depending on where we keep the uh, inverter switching threshold voltage, okay, also VIH, VIL, as we shall see, depends on the aspect ratio and actually the ratio of the WIL of the two transistors. We can decide about the value of VIH and VIL very easily, and then we can determine the power, what you call the noise margin. Okay, and voltage transfer characteristic is almost resembles that of the ideal inverter. Okay. So before we take up the uh, current voltage characteristic, let us briefly discuss about. See, these questions are frequently asked. Okay, at time of your interview. That means the CMOS process and the latch-up process. CMOS process, why is it more complex than standard NMOS only process? Here earlier we saw that both of the transistors were either NMOS transistor. Okay, so the process complexity was minimum. Okay, you can have a fewer number of masks. But now with the appearance of MOS transistor in addition to the NMOS transistor, the the process, that means the fabrication process, assumes some complexity. Let us quickly look into this. We shall not go into deep details, however. Okay, so in order to fabricate both NMOS and PMOS transistors on the same chip, what one does, one can build either N-type tub or N-type well, in which we can manufacture the PMOS transistor, okay, or a P-type tub or a P-type wafer, okay, or P-type tub on N-type wafer. So you can have the underlying wafer to be N-type, on which you can build up a P-type, a P-type well, okay, and build a NMOS transistor there. Now, in general, you know that the mobility of NMOS transistors is higher than that of the PMOS transistor. So, if you build up a a P well, and inside you build up the NMOS transistor, then the mobility within the N well, actually mobility becomes somewhat less rather than it would have been in the underlying substrate. I don't know the actual reason. So thereby what we can do, the mobility of the two transistors may be somewhat nearly equal, but not exactly. Okay. NMOS transistor mobility is always higher than that of the PMOS transistor. Now we describe the procedure of fabrication of first depositing a N-well region, okay, and then how to generate the fabricate the transistors and define the different conducting layers. So first what we have got a underlying substrate, lightly doped p-type substrate. Lightly doped means maybe less than equal to 10 to the power 15 per cc, so many ions per cc. And then what we do, the first mask will be that of the N-well. So you uniformly cover it with oxide, etch out the oxide based on the area need to be there for the N-well region. So there you deposit N-well region, okay, by ion implantation. Okay, so that means you put the pentavalent impurities like say phosphorus or antimony, right? So the first lithographic mask defines the N-well region. Phosphorus, the donor atoms, are implanted through a window in the oxide. So you open a window by etching out sufficient amount of the what do you call field oxide, okay, right, the silicon dioxide, okay. So then you build up the N-well. After the N-well is created, now the active areas for the two transistors, that means in the N-well you will build up the PMOS transistor, in the substrate you will build up the NMOS transistor. So masks of the those transistors should be defined. Okay. So what we do, a thick field oxide is grown on the in areas surrounding the transistors active regions, right? So that means here you can probably the fox we are not able to show. Yeah, it's a complicated picture. Anyway, so wherever the active regions means the inversion regions first of the p-type transistor and the n-type transistor, wherever they are not present, you put up the you pour field oxide, okay, thick field oxide, right? So a field oxide is grown in areas surrounding the transistor's active region, and next a thin gate oxide is laid on top of the active regions, and the polysilicon layer is deposited using chemical vapor deposition or CVD in short, and patterned by dry plasma etching. Okay. Now the polysilicon lines function as the gate electrodes of the NMOS and P transistors, and they are interconnects also. So the we take resort to the self-aligned polysilicon gate mask. Okay, so they will act as the self-aligned masks for source and drain implantations that follow this step. So using a set of two masks, N plus and P plus regions are implanted into the P-type substrate. So into the N-well region, you put the P-type acceptor impurities like boron or indium, okay, trivalent impurities, and here you put the pentavalent impurities like phosphorus or antimony. And of course, based on the precisely defined mask, what is the extent of source and drain, both for PMOS transistor and NMOS transistor. Also, the ohmic contacts is no less important. Ohmic contacts to substrate and N-well are implanted into this step. These ohmic contacts here, they have got a salient role to play. Here we show the N-well contact. N-well contact means within the N-well, PMOS transistor will be fabricated, and surrounding it you have a N-well contact. Okay, so these and the source of the PMOS transistor should be connected to power supply voltage. Okay, so they will establish good isolation. Also, they will lead to some what you call the decrease of the impedance offered by the N-well. Similarly, here also on P plus region, I have not shown it, but this is the ohmic contact. Ohmic means the resistive contact. Okay, so that means non-rectifying contact. So this contact for the N-channel transistor, this also is laid. Okay, so this and the source of the NMOS transistor should be connected to ground. Okay, this is about the process complexity. Okay, so this is the, you can say this is a price to be paid in order to get this advantage. Like the advantages of CMOS inverter is prominent, these two advantages. So in order to realize this, first price to pay is a process complexity. Okay, so that is no less, I mean, more complex compared to what is required in case of trying to build up the NMOS based inverter, purely an NMOS based inverter that we have seen earlier. Second factor, that is also unavoidable, and this let us see in a bit of details. This is the latch-up phenomenon. Latch-up phenomena is quite important. This is unavoidable. This is due to the generation of low impedance path in CMOS chips between the power supply rail and the ground rail. And this stems from the appearance of parasitic bipolar junction transistor. One is NPN, the other is PNP. So for your benefit, we have drawn the cross section of the CMOS inverter as it is built up. So this is the N-well where we fabricate the PMOS transistor, and in the underlying substrate, we build up the NMOS transistor. Note carefully that, okay, so this gives rise to two parasitic transistors. One is the PNP. PNP comes from where? The emitters come from the source P-type a source region and P plus type of drain region. So these forms the emitters of the bipolar junction transistor. And the base corresponds to the N-well, and the underlying substrate corresponds to the collector. Okay, so PNP transistor. Okay, and it is a vertical transistor. So vertical transistor means it will have a good amount of current gain based to collector current gain that is no less than tens to hundreds. Okay, the vertical PNP transistor. Next, we have got the parasitic NPN transistor. How it is coming up? You see, the again it is a two emitter transistor, but it is lateral in configuration. N plus the emitters come from the source and drain of the NPN. The NMOS transistor, field effect transistor. P comes from the underlying substrate and N comes from the NOL. So this is like a lateral transistor, but as this is a lateral transistor, is based to collector current gain beta. So we say that this is T2 and T1. So beta 2 is not as high as that of PNP T1. For TNP, the beta value is quite high, nearly several hundred it can be, but this is a lateral or horizontal transistor. So its beta ranges from a few tenths to just a couple of some tens, 20 or 30, something like that. Also, you see, so basically, these BJTs, bipolar junction transistors, form a silicon control rectifier with positive feedback, four-layer silicon control rectifier. And when they become active, they can virtually short circuit the power rail to ground. And then this can cause a huge current flow and eventually they can damage the circuit. But of course, the designers take proper what you call measures in order to reduce their damaging effect. Let us see how. First of all, again, let us see the equivalent electronic circuit, which is due to the ACI formed by these two parasitic bipolar junction transistor, the NPN that is T2 and the PNP that is a T1. Okay, and also you see the what is the impedance resistance offered by the NWL and the substrate. The NWL can offer this is lightly doped NWL, okay. It can offer a resistance quite high, say 1 kilo ohm to 20 kilo ohm. On the other hand, the substrate resistance, this can be if we have only a lightly doped P minus substrate, that means 10 to the power 15, then it will have sufficiently high resistance value, say maybe hundreds of ohms. But if you build up a P-type, lightly doped P-type epitaxial layer on top of a heavily doped P-type substrate, this combination can tend to reduce the overall resistance offered by the substrate. So it will be not much high. It will be say a few tens of ohms or say hundreds ohms, maybe a few ohms. Okay. Now, why it is required to keep the substrate resistance and for that matter, NOL resistance also lower? We shall see now. For before that, let us see how the latch up occurs. So this is the positive feedback connection, as you can see. Okay, the drain of the this is N type. So the N channel transistor, the drain is this output voltage. Okay, similarly for the P type transistor. Okay, this is a this is NPN transistor. So this is the N type drain of the NMOS transistor, and this is a for the PNP transistor. This is the drain of the PMOS transistor, PNP. Okay, so these two are connected together, but we are showing them separately. Also, the N plus source and the P-type source of the PFET are shown. Now, in general, the collector current of this T1 and T2, in normal operation, they are not dominant. Okay, the BJT effect is quite, you say, insignificant in a normal operation. But something can take place like sudden increase, different ways the latch up can happen. Let me just point out. So suppose suddenly the power supply voltage, okay, this has a overshoot. Okay, it goes above the nominal value of the 5 volt or 3.5 volt, whatever. This can happen due to various factors like, say, it is placed in, say, different, say, lightning occurrence, or if it is placed in some, the circuitry is placed in spaceborne device, okay, in some spacecraft. So there are some alpha particle radiation or cosmic radiation can take place. So various reasons are there. Even there can be various large many devices are there. So sudden spikes or voltage spikes can take place, and that means this power supply can go above the nominal value. Also, the ground level can go below the level. So that means overall, this can lead to a overshoot in the collector current. Okay, of either PNP or NPN or both. And note the result is that because of this connection, suppose the collector current of T2 grows very high, then this will cause a drop. See, note that in general, the these two transistors are off, okay, in cutoff condition. But due to sudden fluctuation of the power supply and ground voltages, or due to radiation based EHP generation, that means the electron hole pair generation, suddenly collector current starts flowing in whatever way, in positive or negative direction, whatever. It will lead to a drop across the resistance offered by the well, also drop across the resistance due to the substrate. And if then a sufficient drop takes place across this will lead to a coming up of this NP transistor as well as the PNP transistor. So once this collector current becomes flowing corresponding to the active region operation of the T2 transistor, it will lead to a setting up of, it will lead to conduction of this transistor T1. So once either T1 comes on or T2, it will lead to the conduction of the other. And this will be a sustained operation. That means both T1 and T2 will be conducting sufficient current. The mathematical requirement is that the product of beta 1 and beta 2 should be greater than 1. Okay, we are not going to details of that. Then you have the concept of holding current. Okay, we hold, I hold, and then the SCR curve, you know that this will be like this. Okay, so it can be sustained current and high range of current. So that will be detrimental to the operation of this CMOS inverter, where the field effect should be dominant rather than the PNP rather than the bipolar junction transistor operation. Okay, so this is how the latch up occurred. So what we have written here, to examine the latch up R well and R substrate, okay, is large. Nominally it is quite large. The circuit is open. That means neither the T1 nor T2 is conducting. Okay, and collector current is just kept restricted to the reverse bias current, the CV, that means the collector based junction, reverse bias PN junction. But if the collector current of one transistor is temporarily increased due to external disturbance, due to radiation or whatever, the feedback loop, positive feedback loop, multiplies this current, triggering of the silicon control rectifier. Once triggered, each transistor drives the other transistor with positive feedback, eventually creating and sustaining a low resistance path between the power and ground rails. This results in latch up. Latch up is definitely undesired. Okay, because the bipolar junction current takes place, tries to dominate over the field effect current, and also current can be uncontrolled. Okay, so heating will take place and eventual damage can take place. There is a possibility. Okay, so some of the causes we mentioned here, when input or output signal swings either far above VDD or far below ground, large currents in the parasitic silicon control rectifier in the CMOS chips can occur. Then sudden transitions into power or ground, okay, buses due to simultaneous switching of many drivers can turn on a BJT in SCR. Then the leakage currents in well junctions can cause large lateral currents. Radiation due to X-rays or alpha particles leads to generation of electron hole pairs or EHPs in short in the say N well or the P-type substrate. The various reasons are there. And how to
Sir,
avoid the latch up? Yes, yes.
sir, why the vertical BJT has a higher current gain than the lateral one?
Okay, Ankit, I'm not able to tell you the details. Okay. In general, the vertical bipolar junction transistor demonstrate higher beta values than the lateral value. But why exactly? Yeah, one reason I can tell, but you please verify. All of you please verify. We see that what is the basic operation of the bipolar junction transistor? Emitter should be much, as far as the doping concentration is concerned for a bipolar junction transistor. The emitter has the highest range of doping, right? Density of carriers. Say for NPN transistor, look at a T2. right? So, and the base region should be, its width should be restricted. That means very less recombination should take place within the base region. The base is there only to provide some mechanical support. And of course, so that the maximum amount of the carriers which are emitted from the emitter, and thereby it's called, the terminal is called emitter. So less amount of recombination in the base region, more amount of collection in the collector. So our the BJT is mostly a current, the current gain is more important. Okay, right. Whereas in field effect, the voltage, the two simultaneous voltages, lateral and vertical, okay, due to this current flow takes place. But the current effect is more prominent in BJT. So out of the emitter, when the carriers are emitted into the base region, less amount of recombination and more amount should be collected. But in case of such lateral device, what I guess is that the base is quite wide. And if it is wide, then a lot of recombination takes place and most of the carriers can lose their existence. Very little amount of current is, very little amount of carriers can find place in the collector. So the base to collector current gain is limited. Okay, as we have just noted that for lateral or horizontal transistor, okay, base is quite wide with respect to the emitter. Okay, so then most of the recombination takes place, and as a result, the current gain is very limited. So the beta value is maybe may go less than one. You'll be surprised, or a few tens of ohms. But in case of NPN transistor or vertically generated, vertically fabricated junction transistor, the base width is kept to be within a limit. So that in base, okay, base provides the region in which the and there is relatively lightly doped. And definitely the for in order to get the emitter injection coefficient, there is a term, if you remember, and also the the base to collector current gain, in order that that has got a very large sufficient value in hundreds, it can go up to the 250 or 300 like that. It is kept, the beta, the base width is kept to be small. In fact, beta varies inversely with the width of the base. Probably you have seen in your first or second year class when you studied about the introduction to electron, right? So the beta value varies inversely with the width of the base. So when the vertically, from the vertical, here the vertical PNP transistor, it can have a value, large value of beta. Whereas the lateral or the horizontal transistor, where the base is quite wide, it is unavoidable when you are building up the transistor in this fashion. So the beta value falls. Okay, it can be just a few tens, or it can go below one, right? So this is my very what you call crude explanation as why the lateral transistor has much lower beta compared to the vertical transistor. But Ankit and dear friends, please study if you want to know in details why vertical transistor provide higher beta than the lateral transistor. Okay, Ankit. So I am not able
Yes,
to
sir.
tell you in
Okay, sir.
details, right? And so what we do, just let me mention some of the measures that we may take in order to reduce the effect of latcher. Probably overall we cannot remove it, we cannot write it off, the latcher phenomenon. Some of the mechanism is that first reduce the gains of BJTs by lowering that minority carrier lifetime. So minority carrier lifetime, if you want to reduce, then you have to build up more traps, need to more generate more, process for more recombination. Then we have to build some gold doping, which will act like the traps for the minority carriers. Okay, by reducing the minority carrier injection efficiency so that we don't want the BJT effect to take prominence over the field effect, or by using Schottky source drain contact. Schottky barrier, that Schottky barrier hardly allows the transistor to go into saturation. Its operation is restricted to active region and cutoff. Scarcely ever they go to saturation. So that by current will be limited. Then use P plus guard rings connected to ground around NMOS transistor, or N plus guard rings connected. In fact, the whales also will be like that to reduce the resistance of the whale. So guard rings means the resistance offered by the whale as well as the resistance offered by the substrate will be limited, will be quite limited. And to capture the injected minority carriers before they reach the base of the parasitic BJTs. and also place substrate and well contacts as close as possible to source connections of MOS transistors to reduce the value. Okay. So these are several mechanisms. So a brief introduction to the latch up. Okay, so that latch up and the process complexity are the prices to pay in order to reap the benefits of CMOS inverter over the other, namely zero, I mean virtually zero DC power distribution and very sharp noise margin. But let us now see about the DC characteristic and how the voltage transfer curve is generated. As you can see, this mimics as if a what you call a sharp type of the ideal inverter. What will show? It will go right up to 50% of the VDD, comes down sharply, and then fills up the lower half of the output voltage. Okay. So the CMOS inverter, the VOH would be exactly VDD and VOH will be exactly ground. But in order to see how the different regions of operation come into being when we are applying a gradually incremental input voltage. Okay, so we'll have in general 5 salient regions. And also what we have drawn 2 straight lines. You see, with unity slope. See that the equation of this line, straight line, which is situated towards the right. Here you are getting the operation of the NMOS transistor, and write like this: V out equal to V in minus V2. V out is nothing but the drain to source voltage of the NMOS transistor, and V in equal to nothing but the gate to source voltage of the NMOS transistor. So if you write like this, VDS equal to VGS minus VDON. Okay, so whenever VDS exceeds VGS minus VDN, the NMOS transistor goes to saturation. That means if you draw this unity slope straight line, which intersects the horizontal voltage axis at this point. Okay, so with V equal to 0, obviously V out equal to minus V2. That means if you extrapolate this, it will cut the vertical axis at minus VTON. That is sure. So obviously the parts that when the operating regions, when the operating points will lie for any operating point, when it will lie above this straight line, will conform to the case when NMOS transistor is in saturation. That's why we are giving this notation. Okay, and the second straight line, as you can see easily, it corresponds to V out equal to V minus VTOP. And note that VTOP, that means the threshold voltage of the PMOS transistor, is positive. So hence the supply, hence the slope on the voltage axis is positive here. So when V in equal to 0, V out equal to minus VTOP. So that means some positive value. Okay, right? And if suppose VTOP and VTON are numerically equal, then they will be parallel and equal magnitude of slopes on the vertical axis will result. Anyway, look into the fact that if you can rewrite this, the drain to source voltage of the PMOS transistor is like V out minus VDD and VGSP equal to V in minus VDD. So if you rewrite this, you will get like this: VGSP equal to VDSP minus VTOP. Now we know for sure that PMOS transistor will be in saturation when the VDSP is less than VGSP minus VTOP. So obviously all the operating points which lie below this straight line, this second straight line on the left, will correspond to the region of operation where PMOS transistor is in saturation. So obviously the common regions, that means if you get, so the where you get these crosshatch regions is like a parallelogram. Okay, so here this region will be the region where both the transistors are in saturation. Okay, so in fact the CMOS inverter will pass through these regions. The medial region is one C, denoted as C. It will be the region where both the transistors will be in saturation. And as you try to increase the input voltage from very small value before it reaches the threshold voltage of the NMOS transistor, and this region is called A. Here the input voltage is numerically less than threshold voltage of the NMOS transistor. Here the PMOS transistor provides a good channel, right? So it can hold the output voltage close to VDD, and almost equal to VDD. And NMOS transistor, however, will be cut off. PMOS transistor will be in linear region. Then as the input voltage goes past the threshold voltage of the NMOS transistor, what happens? The NMOS transistors comes on and it is in saturation level, because it will provide quite a lot of resistance. However, the PMOS transistor offers very small resistance, so this plays the role of a driver. It can pull the voltage towards the higher side. Okay, so this is the range that means uh, which we call it to be B, and typically VIL, where the dV of dV equal to -1, that happens in the region B, that is found in the region B. So here typical input voltage is VIL, output voltage is quite high, NMOS transistor in saturation, barely in conduction, but the PMOS transistor is quite firm in the conduction. Okay, it is strong in conduction. Then you reach the region C, where both the transistors are in saturation. Typical typical input output points will be the inverter threshold voltage. So if you draw a straight line intersecting the origin, so it will pass through region C, and at the point when it intersects the VTC, input and output voltage are equal, and this will be the what you call inverter threshold switching voltage. Okay, which we write as VM or VS. In your book, you may find it written as VTH, but just to minimize the confusion with this, with the technology threshold voltage, VTON and VTOP, we can write it as VM or VS. And both the transistors are in saturation. Then you continue to increase the input voltage. The next region of operation is D, where the NMOS transistor will become dominant in conduction. So NMOS transistor passes in linear region, PMOS transistor in saturation. VIH, where dV of dV equal to -1. VIH is a typical input point. Output voltage is quite low. It is numerically above VOL, okay, about 0, but quite low. So here at region D, in region D, NMOS transistor is in linear region, PMOS in saturation. And finally, you pass to E, okay, where current has stopped, rail to rail current, DC current is not there, 0, because PMOS transistor has gone into cutoff region, and NMOS transistor is in linear region. So normally region A and E are the regions where current is 0, and these are the stable states, A and E. Okay, so this is quite obvious to you. In steady state operating regions corresponding to regions A and E, the first and fifth region, current drawn from power supply is 0. CMOS inverter can drive any load. Okay, that is the fan out logic gates and interconnect capacitance by supply. So that means if you are to charge up a load, only the NMOS transistor will be conducting. Okay, and it is firm in conduction, so it can provide fan out logic gates. Okay, a large number of gates it can drive, and also interconnect capacitance by supplying current to the load, sourcing current. And on the other hand, when you are in region E, the NMOS transistor will be instrumental in discharging a capacitive load, and for that matter, that means any number of logic gates. Okay. Next, what we do. So this, I think up to this it is clear. Next, what we take up, calculate the VIL. Note that neither the NMOS transistor nor the PMOS transistor suffers from the substrate bias effect, because source and body are shorted for the PMOS here, and source and body are shorted for the NMOS transistor. So both of them will display zero bias threshold voltage. Slope of the voltage transfer characteristic is -1 at input voltage equal to VIL, where NMOS is in saturation and PMOS is in linear region. So writing the corresponding current equation, we get like this, differentiating both sides of the current voltage equation with respect to V in, and setting the dV of D equal to -1, we get this as the equation 4 and equation 1. Okay, so I mean you can rewrite this in this manner: VIL equal to dV of and this again the ratio K we shall see in details. K are equal to Kn by Kp, Kn equal to mu n COX into W by L of the NMOS transistor, and Kp equal to mu P into COX into W by L of the PMOS transistor. So one must solve equation 2 and equation 5 together simultaneously in order to get the numerical value of the VL and VL. And no iteration is required. You get it at one go. So here the solution procedure is quite straightforward, requires no iterations as in the previous case, since none of the two transistors is subject to body bias effect. Next, you see is very similar for the VIH. If you recall, in the BTC, for at Vin equal to VIH, the NMOS transistor is in linear region where the PMOS transistor is in saturation region. So you write the Kirchhoff's current law equation at the output node in that manner. Okay. So and differentiate that equation with respect to input voltage. Set dV out D equal to -1. You get the expression for VIH. So this is a close relation between VIH and Vout. Implicit relation, direct relationship. So you solve equation 5 with respect to equation 2, the current voltage equation, in order to solve for VIH and Vout. So you can solve them simultaneously, the two equations. Okay, I believe no doubt. Next we see the fifth salient voltage where input and output voltage are same. So that happens at the intersection of the voltage transfer characteristic curve and a unity slope straight line passing through the origin. Okay, with so that means inverter threshold voltage is defined as that Vm equal to Vin equal to Vout. M stands for the middle. Okay, so for ideal inverter, Vm should be in the middle of the, let's say, VDD by 2. It is important that CMOS inverter should exhibit large noise margin and a sharp VDC transition. And of course, both the transistors are in saturation. You can convince yourself by seeing that VDS is greater than VGS for the NMOS transistor, and also VDSP is less than VGSP minus VTOP for PMOS transistor. So hence, both the transistors are definitely in saturation. Okay, and you write the current equation. Then what do you do? Straightforwardly solve it, because input voltage and output voltage are equal. So set VGSN equal to VGSP equal to V. Okay. Actually, VGSP equal to V minus VDD. I'm sorry. Then you take to solve for V, take the positive square root on either side. Okay. Then you uh, putting in V equal to Vm and K, the transconductance ratio is equal to Kn by Kp. We can write in this fashion. Okay. So this is the expression for switching inverter switching threshold voltage. It is equal to the technology threshold voltage of the inverse transistor plus root over 1 by Kr, where Kr equal to Kn by Kp multiplied by VDD plus VTOP. Note that VTOP is a negative number, okay? Because this the threshold voltage of a PMOS transistor, which is always negative. Note that the inverter threshold voltage is defined as this Vm equal to V equal to Vout. When the input voltage is equal to Vm, however, the output voltage is found to attain any value between Vm minus VTON, or yeah, so that is for sure. So without violating the voltage condition. So that means it will be in region C, and the range of output voltage will be Vm minus VTM to Vm minus VTM. This is because the VTC segment corresponding to region C in figure becomes almost vertical. Okay, so output voltage may not be fixed right at Vm. It will vary from the range Vm minus VTN to Vm minus VTOP. Okay, so if channel length modulation is neglected, that is lambda equal to 0, why? Because lambda will be may take prominence while both the transistors are in saturation. So if you neglect it, as lambda is a few tens of volt, so we see that this is the overall range of the output voltage. Next, what we see, a brief discussion on the Kp by Kn. The Kn by Kp, you see, these are Kr. Okay, the transconductance ratio, and you have written for sure. Now, for you see, suppose this is the nominal value of Kr. Now, if you keep L by Wn fixed, and if you decrease L by Wp, what happens? What happens? As you can see, low to high conduction of Vout happens earlier. That means the resistance offered by the PMOS transistor is less. Okay, so if resistance offered by the PMOS transistor is less, so low to high transition. Note that while we are bringing down the input voltage from the higher side, so as you go towards the lower side of the input voltage, okay, and it's an inverter, so low to high transition of the output voltage will be affected. Okay, and it is a role of the PMOS transistor. Now, if you decrease L by WB, thereby decreasing the impedance offered by the PMOS transistor, so low to high transition of output voltage will be fast. Okay, that means as you decrease input voltage from a high value towards the lower side, okay, And if you decrease the impedance of the PMOS transistor, then the low to high transition will be happening higher, faster, earlier. So that's why the curve will shift towards the lower, to the right side. Okay. Now, if this be the অনুরাগ একটু ক্লাসে আছি, একটু বাদে ফোন করছি, হ্যাঁ এই ক্লাসে আছি, হ্যাঁ শিওর, ওকে, থ্যাংক ইউ। So you see that as you decrease the input impedance, the impedance offered by the PMOS transistor, okay, right, and you are going from higher value to lower value of input voltage, then the VTC, the VTC curve will be shifted towards the right, whereas it will be, and correspondingly you can reason similarly, you find that the VTC curve will be shifted towards the lower, towards the left. As you increasing VR means how we can increase, okay, so increasing VR means you can decrease the L by WP. So relatively, the relative impedance offered by the NMOS transistor will decrease. Okay, and NMOS transistor is instrumental is in bringing down the output voltage. So for earlier input voltage, it will lead to a drop in the output voltage. Okay, and as far as the variation of inverter switching threshold voltage as a function of transconductance ratio is concerned, just take to that equation. Suppose we want to make it say 1.65 volt. So 1.65 volt means what? VTON equal to 0.6 volt. Say, suppose I take the some typical value, VTOP equal to minus 0.6, minus 0.7 volt. Suppose the power supply voltage is 3.3 volt. Then if you want to make a VDD right at the middle, that means 1.65, it will be necessary that KR equal to 0.82. So accordingly, okay, you can choose a W by L ratio of the transistor. Okay, right. The transconductance, that means the variation of, if you vary KR, you can dictate, you can determine, you can control the value of the switching threshold voltage. Okay, so from that, from the expression that we derived earlier here, okay, why varying KR? So KR is an independent variable, VM can be varied because the earlier other values are fixed, VDD, VTOP, VTN, all are fixed. So in your hand as control element, you have got KR. So with varying KR, you can control the variation of the switching threshold voltage, right? Okay, so here actually for one VM equal to 1.65, and the given value technology threshold voltage of NMOS and PMOS transistor and power supply voltage. So required KR equal to 0.82. Okay, so you can take the proper value of the W by L of P and W by L of NMOS. So any question, dear friends? Yeah. So let me see. I need to take the attendance. Yeah.
We have enough class.
Oh yes. Any question? Yeah. Yeah. Ogit and Abhishek. Anyone? Alex.
No, sir.
No,
I
sir.
don't
I
have
don't
any
have any
questions.
Okay. Yeah. Yeah. So anyone? Any question, dear friends? Okay. Well, I'll upload this material after some time on MST. And yeah. So if there is no question, okay. Thank you for your attendance, because I think you have got a class now, na, from 11 o'clock. Okay.
Yes, yes, sir.
Yes, sir.
Okay. Okay. Thank you, dear friends. Stay safe. Stay healthy. We'll meet next on Monday at 10 o'clock. Okay. So yeah, I think you can leave for the next class.